That's the angle between a line and the axis. But we're interested in the angle between two lines, okay? So you're going to need to draw a new set of axes underneath here. You may remember a little while back we were doing work with the sine rule and the cosine rule. We were proving a bunch of things about it. In particular with the sine rule, we proved that, make sure I write it correctly, A on sine A is equal to B on sine B, etc. But the reason why they're all equal to each other is because, does anyone remember why they're all equal to each other? It's because they're all equal to something else outside of them, namely the diameter of the circumcircle. That's right. So you can write that as that. Okay. Now, when we did that, we had to go to some length, and we went through three cases. We looked at acute versions of the angle, right angle, and the obtuse. Okay. Now I could do the same thing with what I'm about to do right now. Okay. But I'm just going to illustrate it with one, and I'll leave it to you to have a think about how it can apply it when you have slightly different cases. Okay? So on here, let's draw two lines. Okay? Now on here, I'm interested in, I should put a little bracket here, not just the angle between two lines, but a specific one, the acute one. Okay? Because when you put up two lines together, unless they meet at right angles, one angle will be acute and one will be obtuse. Okay? Now on the diagram that I have drawn, the angle is there, the acute angle, okay? But depending on the way you've drawn it, perhaps it's actually this angle, right? Either one of them could be the acute angle. As you will see, these are the different cases that I was talking about, but what we're going to establish works with all of them, okay? Now, if that's that angle there, in order to sort of get from one line and its angle to two, I'm going to need to know what their angles are respectively, okay? So I'm going to call this one over here alpha. Okay, so there's the first one. Oops, I should have named this 1 so it matches up. Sorry about that. You'll survive. Okay, I'll call that one alpha. I'll call this one beta in the corner. Okay. Now I've got these lines labeled with their equations, which are somewhat arbitrary. To be honest, I don't know what they are, and it doesn't matter. I can still work with them even if I'm not sure what they are. Okay. Now I want you to have a look at this triangle. See how you have here, in this triangle here, you have what we call an exterior angle. That's an exterior angle, right? It's outside the triangle. And we know about the relationship between the exterior angle and the two opposite interior angles. Does anyone know what the relationship is? Yeah, Reynard.
Alpha is equal to theta plus beta.
Fantastic. Whoops. Okay, they do rhyme, don't they? Theta, beta, theta, beta. Okay, now, I've got that, right? But what I'm really after is theta. Do you agree? Like that's the angle between two lines, okay? So I'll just rearrange this a little bit. Theta is equal to alpha minus beta, okay? Now, here's where I'll pause and I'll say there are other possibilities. In this case, alpha is bigger than beta, right? So alpha will come first. If I had two other lines where alpha was smaller than beta, because that would work too, then this would be switched around, okay? And if I go even further, if I just pick different angles, maybe this one's almost vertical, something like that, it could be 180 minus the sum of those, okay? But I'm going to put to you that all of those cases actually are equivalent if you work them through, okay? So now, from there, the reason why this is useful is because we now know maths that can equip us to work out what these things are, okay? I'm going to take tan of both sides. Tan theta equals tan of minus beta. Okay? See that? So, on the right-hand side here, I actually know what this is equal to because I have learned an identity that tells me what it's equal to, right? This is the difference identity for tan, okay? So if you can't remember it, it's tan alpha minus tan beta. If I filled that in, I wonder if you can tell me the denominator. 1 plus tan alpha, tan beta. Fantastic, okay? But from there, I can even go a step further, right? Because, look here, right? If you just forget about this second line for a second, you just look at this one here, m1x plus b1, and its angle is alpha, right? For this guy here, I can say that tan alpha is equal to what we just established before for a single line. It's m1, isn't it? Right? Do you see that? That's its gradient. In exactly the same way, I can say that tan of beta equals m2, right? So I can switch these guys in here. I can just say that's m1 minus m2 all over 1 plus m1, m2. Okay, one last little step, right? I want the acute angle between two lines, the acute angle, right? So to make sure that I get the acute angle, I have to ensure that I stay in this quadrant. You see that? Right? This is where tan is positive. If I cross over here, I'm in trouble. I won't get the acute angle. I'll get the other one, which is obtuse. Don't move. Okay? So to ensure that I get the positive one, all I do is, pulling back to the first topic, slap absolute value signs around everything. Okay? Because that will ensure tan theta will be a positive number, so I'll automatically be in the first quadrant. I'll get the acute angle. Okay? So this here is the formula you can use to find out whatever angle that is for any combination of M1 or M2. Okay?